All right, welcome back, everybody. We are going to finish with the Suzuki and the Heck reactions today. Last time I told you that the Suzuki cross-coupling reaction was between an aryl or a vinyl halide. Just need an sp2 hybridized carbon attached to a halide, and then a boronic acid or boronic ester. That's a boron attached to either OH groups or OR groups. And then you also need the carbon attached to the boron to be sp2 hybridized, either vinyl or aryl. You use a palladium zero catalyst, and you need sodium hydroxide or some base. And you make a new bond between these two carbons, orange and blue. The stereochemistry of the vinyl portion is preserved. That is, if the boron is trans to the methyl group, the new carbon-carbon bond is trans to the methyl group. So in terms of predicting products, the Suzuki reaction is easy once you recognize it as a Suzuki reaction, because you just have to identify the carbon bonded to the bromine, the carbon bonded to the boron, and then you just stick those two together and you don't change the stereochemistry of the vinyl group. We talked about the mechanism, and we monitored oxidation state of palladium going through the mechanism. And this isn't something that I necessarily want you to have to be able to produce from scratch, but I do want you to recognize reductive elimination and oxidative addition steps. As we talked about last time, the thing that you put into the reaction isn't necessarily always the active catalyst. We could tell that was the case for this 4-triphenylphosphine palladium species because it's coordinatively saturated with 18 electrons total. It loses 2 ligands, and then you get to this palladium zero species that only has 14 electrons. There's plenty of space for new ligands, and then an oxidative addition step happens. And recall, in that oxidative addition step, we add 2 ligands to the metal. That's why it's an addition step. Of the 2 new metal ligand bonds, one of them comes from the electrons in the carbon-carbon bond, and the other comes from the electrons from palladium. You can't tell which, and that's why nobody really pushes arrows for this reaction. If you look at that complex, it's got 2 L ligands, 2 X ligands, so it ought to be palladium 2+. That means there's 8 d electrons and 16 electrons total. What happens next is a reaction called transmetallation, a step called transmetallation. We're not worrying about the arrow pushing for that step. It hasn't been worked out in a lot of detail. What people seem to know is that hydroxide attacks the boron to make this tetra-substituted boron species with a negative charge on the boron, and then the boron and the palladium trade ligands. This yellow carbon on the vinyl group ends up bonded to palladium, the bromine ends up bonded to boron. Now you still have a palladium 2 species, but now you've got 2 X-type carbon ligands, and now we're ready for the reductive elimination step. In the elimination step, we're going to make a new carbon-carbon bond between the phenyl ligand and the vinyl ligand. Of the 2 electrons involved in the metal ligand bonds before that step, 2 of them become the new carbon-carbon bond in the product, and the other 2 go back onto palladium. That's why it's called a reductive elimination. Electrons that used to not belong to palladium now are given back to palladium, which is now a D10 metal. And that's the Suzuki reaction. So, questions about oxidative addition, reductive elimination? Okay, so let's do a little bit of predict products, a little bit of synthesis with the Suzuki reaction. There are, of course, making aryl halides is easy. You know how to do that. We've learned how to do that in 352. So one of the best ways to install a halide is just the aryl halogenation reaction that you learned in an earlier chapter. If you want to get fancier, you could maybe make something like this. How would I make this from benzene? What do you think? Anybody remember? We know how to put halides on. What about methoxy groups? Oh, that's something from chapter 22, which you were hoping to forget about. That's the diazonium chemistry. I don't know if you guys remember that. Remember that if you do aryl nitration, we could get the para-substituted bromo-nitrobenzene. Then you could, looks like we're going to need some more space. Then you could reduce the nitro group using palladium catalyzed hydrogenation to the aniline. Anybody remember what comes next? The thing with the triple bond, sure. What's the reagent? It's sodium nitrite, which converts the aniline into the diazonium salt. And it's at that stage that you could, I'm still not quite there. I think the way your text has done this in the past is you use hydroxide to do a reaction, a substitution reaction, where the OH replaces the basically diazonium nitrogen leaving group. And then you can do an ether synthesis reaction where you deprotonate the phenol and then add some methyl halide like methyl iodide, and that will do the SN2 reaction to give you the para-methoxy-bromobenzene. Okay, so that's a fun review of things. Fun, quote, fun review of stuff. That's one way, those are a couple different ways that you can make aryl halides. Of course, sometimes you can also use diazonium chemistry to install halogens. So supposing we had a bunch of other functional groups and it wasn't convenient, we couldn't get the right regioselectivity using aryl halogenation, we could have used copper bromide on the diazonium ion to install the bromo group. Let's talk about the boronic esters. There are a few ways to make boronic esters, which are important reactive partners in the Suzuki reaction. A simple way is to take an organolithium reagent like this phenolithium and react it with a boron reagent where the boron is attached to 3 methoxy groups. And what happens here, we won't draw the full mechanism because it doesn't matter that much, but just to give you an idea of what's happening, the organolithium reagent delivers a negatively charged phenyl group to the boron, and you get an intermediate that looks like this, where boron is attached to 4 different things and has a negative formal charge, and one of those methoxy groups leaves, and you end up with the desired boronic ester reagent. Any idea where to get the phenolithium reagent from? That's phenyl bromide. That's a reaction all the way back from chapter 13, back in January, which we can't even remember anymore. All you do is you take the aryl halide and you add lithium metal. That reaction is called halogen metal exchange, and we didn't learn the mechanism for that. It wasn't particularly important, but that's sort of how the reaction happens. And of course, as we just showed above, you can get the halide from aryl halogenation. So that's one synthetic pathway you can use to generate Suzuki reagents pretty simply. Another is hydroboration of alkynes. So those are two things that you haven't heard too much about since 351. Hydroboration adds a carbon-hydrogen bond and a boron-carbon bond in the place of a carbon-carbon pi bond. So as an example, you can take this terminal alkyne and you can add a hydroboration reagent. Typically when you did hydroboration in 352, you used BH3, but you were also told that some other reagents with just one boron-hydrogen bond can do hydroboration chemistry as well. Here is one of these, and it's called catechol borane. That's not really important, but the key portion of the molecule is this boron-hydrogen bond. What happens is the pi electrons in the alkyne attack the empty p orbital on the boron, and they start to make a new carbon-boron bond first. They make the bond preferentially with the less substituted carbon. You make the carbon-boron bond preferentially with the less substituted carbon because in the transition state there'll be a buildup of positive charge on the more substituted carbon where it's more stable. Then the boron-hydrogen bond breaks and gets delivered as a hydride to the less substituted carbon. And that gives you this product where the new carbon-boron bond and the new carbon-hydrogen bond have been delivered to the same side of the alkyne. And then you can use that directly in the Suzuki reaction. In 351, we often wanted to go on and replace that carbon-boron bond with a carbon-oxygen bond. That was hydroboration oxidation to generate alcohols. But in the case of preparing for the Suzuki reaction, that's good enough because that's where we want to end up. So those are two different ways of making a Suzuki reagent to prepare for the Suzuki reaction. All right, so let's do a little bit of predicting products. All right, so start with this alkyne, and your text uses the catechol borane reagent. That's going to convert that terminal alkyne into the following boronic ester. Notice that the hydrogen and the boron end up cis to each other. But notice that the boron is trans to the carbon on the other side, that pi bond is E. When we do the Suzuki reaction, we're going to preserve that E stereochemistry. So next, we'll use the typical reagents for the Suzuki reaction. Palladium with 4 triphenylphosphine ligands, and then sodium hydroxide. And then the other partner is going to be this vinyl halide. Notice that in the vinyl halide, the carbon that's attached to the bromo group already has a methyl group on it, and that bromo group is trans to the methyl group. We would say that this alkene is also E. So we're going to make a new pi bond between the orange carbon and the green carbon. Sorry, we're going to make a new sigma bond between the orange carbon and the green carbon. So once you got an idea of what the Suzuki reaction is, predicting the products is not hard. The new bond goes there. We preserve E stereochemistry on this side. That was the green carbon. And then on the other side, here's the orange carbon. The orange carbon has a methyl group on it. And then on the other side of the alkene, trans to the red bond, you also have a methyl group. And that's the product that you form. So Suzuki reactions can make dienes, starting with when you start with a vinyl boronic ester and a vinyl halide, you can make a diene. And you learned some things in 351 that you can do with dienes, and we'll review that a little bit later today. Okay, questions about that? Yeah?
So from the triple bond on the left, does it always create a trans configuration?
Yeah, hydroboration creates a trans configuration. Yep.
And then that's preserved throughout the rest.
And then that's preserved, yep. Yeah, and the reason it creates a trans configuration is it's a syn addition of the hydrogen and the boron across the pi bond. Yep, others? Okay, let's do another. So this will be with a reagent that we made above. Only this time, I don't want this to be the aryl halide in the Suzuki reaction. I want it to be the boronic ester portion. So I need to make the boronic ester. First, I'll do halogen metal exchange with lithium to make the corresponding organolithium reagent. Then I will add the trimethoxyboron reagent to generate the boronic ester. There's only 2 of those methoxy groups left at this point. Then again, the Suzuki reaction using these reagents, and then the coupling partner is going to be this larger molecule, which I need more space for. And as you'll see, the Suzuki reaction is a great opportunity for whoever writes tests to try to overwhelm you with unnecessary detail. For example, if you look at this molecule, you don't have to. Yes, I do. If you look at the 2 molecules, as long as you can identify the boronic ester and the carbon that's bonded to the boron, and then the carbon that's bonded to the halide on the other, you can forget and not pay attention to the rest of the molecule. It's just an R group that's a spectator. Actually, the beautiful thing about the Suzuki reaction is it is tolerant of lots of different functional groups on either side. They don't interfere with the reaction. So you can use it fairly late stage to bring 2 separate parts of the molecule together to make a larger molecule. And as I said, this is by far one of the most commonly used reactions in the pharmaceutical industry. There are lots of different variations on the Suzuki reaction, and we're just showing you sort of one of the most common ones. Here's the new bond that we made between the blue carbon from the aryl halide and then the orange carbon from the aryl boronic ester. This is an interesting bond. The red bond there is interesting because it's between 2 benzene rings. And it turns out that 2 benzene rings directly link to each other. That's called a biphenyl or biaryl linkage. They're interesting because if they both laid flat and conjugated next to each other, if you built a model, you would see that those 2 hydrogens, the sort of ortho hydrogens, would bump into each other. So biaryls actually rotate so the rings are perpendicular to each other, so they don't sterically get in each other's way. Sometimes in some molecules, not in this one, but in some others, that allows for something called axial chirality, which is kind of crazy and which you don't need to worry about. But we don't have any method so far from 352 to make a biaryl linkage, but this is the first. Okay. All right, so that is the Suzuki reaction. Anything else you want to ask about that one? Yeah.
Does the boronic ester just pop right off? Just kind of hang out by itself? Or...
What happens to the boronic ester? Its role is in this transmetallation step where it transfers the carbon to the palladium. After that, I think it picks up a bromo and then it's done. Yep. Periodically, people will, the Suzuki reaction is so great that people have been wondering, can we push it to the point where it doesn't even need palladium? And so there have been papers published where people are like, ooh, look at this cool palladium-free Suzuki reaction. And it turns out that they probably were not palladium-free. The people that did those experiments were using round-bottom flasks that had previously had palladium in them. And even the very, very, very small amount of palladium that was still in that flask was enough to catalyze the reaction. So, I mean, it's cool that the reaction works that well and that you don't need very much palladium at all to make it work. All right, last reaction that we'll do. There were others in chapter 28 and in the study guide, which we are not getting to. You, if you've done those, you'll maybe have a better shot at maybe if those questions show up on the ACS exam. If they don't, you'll just be better prepared for your future if you decide to be in the pharmaceutical industry. But you're welcome to report your completion of the study guide if you didn't do the olefin metathesis stuff and the cyclopropanation stuff. The Heck reaction is the last one, and that actually is the last name of the professor who invented it. And it happened at around the same time as the Suzuki reaction was developed, and they and some others, Professors Heck and Suzuki and another won the Nobel Prize for their chemistry. The Heck reaction is going to look similar to the Suzuki reaction, but there's going to be a couple of key differences. So first, similarities. The Heck reaction, one of the starting materials, like the Suzuki reaction, is an aryl or a vinyl halide. So I don't know why this is my favorite aryl halide today. It's just in the examples I have in my notes a lot. So there's our methoxy group, yay. And then the other partner, and this is where the difference is. The other partner is simply an olefin, not always, but usually an electron deficient olefin. That means one that has an electron withdrawing group attached to it. In this example, I'm choosing an ester. So recall, yeah, go ahead.
Can you explain briefly what an
Olefin is the same thing as an alkene. That's actually a term from the oil refinery. People talk about paraffins, which are high molecular weight hydrocarbons. Olefins are hydrocarbons that have double bonds in them. And chemists sometimes prefer saying olefins instead of alkenes because alkene sounds kind of nasally. So, I don't know. So sorry about that. Yes, an alkene with an electron deficient, with an electron withdrawing group on it. Okay. So notice that in the Suzuki reaction, you could easily tell which carbons to link together, because the one had a bromo and the other had a boron. In the Heck reaction, you can easily tell on one partner because one's got a bromo, but the other partner doesn't really have anything on it to really point out which carbon we're going to form a bond with. It's sort of what we might call an unfunctionalized olefin. It doesn't have a special carbon heteroatom bond that indicates what you're supposed to do. Usually it's this carbon that you form the bond with, but it's also possible to form a new bond with this other one instead. So you should be prepared to think about both possibilities. Most of the time, if you're running a reaction in the lab, it's going to be this one, unless there are some other features of the molecule that make it better and more stable to form a new bond with the other carbon. So let me draw the products of the Heck reaction, or rather, let's do the reagents. This is also another difference in the Suzuki reaction. The thing that you put in the reaction is palladium diacetate. OAC stands for the conjugate base of acetic acid. So this is a palladium with 2 acetate ligands. The way this is typically drawn is like this. Oops. If you take both of those ligands away, the complex is neutral, so if you take both of those ligands away, you can see that it's palladium 2+. In a way, the acetate ligand is what we call a bidentate ligand. It bonds with the palladium in 2 places. On the carbonyl side, it's the lone pairs from the oxygen that are bonded to the palladium. On the negatively charged oxygen side, it's the lone pairs on that oxygen. So acetate is like a dual XL ligand. It's an L ligand on the carbonyl oxygen. It's an X ligand on the carboxylate oxygen. And so because of that, because both of these acetate ligands leave as -0, you can tell that this is a palladium 2 molecule. That would mean it's a D8 metal, and overall the complex has 16 electrons, 8 from the metal and 8 from each of these metal ligand bonds, 2, 4, 6, 8. As I think I maybe mentioned before, maybe that was last hour, sometimes when you do palladium catalyzed reactions, you synthesize the palladium catalyst to begin with, and that's what you put in the reaction. Other times, you don't have to, because if you add the ingredients, the catalyst assembles itself in solution. This is an example of that. You add palladium acetate, and then you add a phosphine ligand. And 2 of these phosphine ligands are going to end up binding the metal. The ligand in the Suzuki reaction was triphenylphosphine. The ligand in the Heck reaction, at least the one described in your text, is almost like triphenylphosphine, only each of the benzene rings has a methyl group at the ortho carbon, which I'm not drawing very well. You could see that that would make a fairly sterically crowded phosphorus. There's a whole side of chemistry that's all about changing the structure of the phosphine ligand and how that influences the reactivity of the metal that the ligand's bonded to. We're not even going there, we're just barely scratching the surface, but there's hundreds of phosphine ligands you can choose from. This is one of them. Your text abbreviates this as P with O tall in parentheses. O stands for ortho, tall stands for this benzene ring that has the ortho methyl group attached to it. Methyl benzene is toluene, so that's where the tall comes from. Lastly, you need a base. So these are the Heck reagents, a palladium 2 source, a phosphine ligand, and a base, which is triethylamine. Okay, so then let's draw the products. Here's the new bond. And you'll see that there wasn't any stereochemistry about the alkene to begin with because it was monosubstituted. Now we put a new carbon-carbon bond with the terminal carbon on the alkene. And this process now introduces stereochemistry, and because of the mechanism, it is selective for the trans configuration of the alkene. All right, so I do want to talk about the mechanism because you may be wondering, if you look at the starting material, there were 2 hydrogens on that terminal carbon of the olefin or the alkene. In the product, there's only 1. Where did that hydrogen go? And I'll show you where that is as we look at the mechanism. Before we do that though, let's just do a couple more predict products for the Heck reaction. You will recognize the Heck reaction, as I said, by noting that one of the partners is just an alkene with maybe an electron withdrawing group on it. And you'll also recognize the different reagents. One is palladium-2, another is this weird phosphine ligand, and then also you have triethylamine as a base. All right, so a couple more predict products. Here is vinyl halide. Here is an olefin. Here's the palladium-2 catalyst. Here's and you can abbreviate the phosphine ligand as PR3, that's fine with me. And then triethylamine. You're going to make the new bond between the vinyl carbon that's attached to bromo. And then you're going to assume most often that the new bond is going to be with the terminal carbon of the alkene, though you won't be surprised if you see it happening at the internal bond in other situations. Here is the vinyl group. Here's the orange carbon. This is the new bond. Oops, that's not what I wanted. Here's the new bond that we make. On the other side of that new bond, you have the alkene that's still there, and we'll selectively choose the trans configuration here. So the Heck reaction leaves the vinyl stereochemistry unchanged, and then it introduces trans stereochemistry for the alkene portion of our starting material. And as before, you'll notice that one of the products that you can get from a Suzuki reaction is a diene, which then allows me to tell my last dad joke of the semester. Help, I'm dying. Yes, thank you. So there are things you can do with dienes that you learned from 351, and I figured it might be good to just review them briefly. Do you know what is one of the famousest things you can do with dienes? Diels-Alder. Those words sound familiar? Diels-Alder was one of the most complicated but coolest reactions from 351. You're able to build up a lot of complexity from simple starting materials. I'm going to redraw this diene that we just made in a S-cis conformation. And groan all you want, but you're the ones been asking me, how can I prepare for the ACS exam? And so now we're going to review the Diels-Alder reaction. So this is the diene. Recall, you need a dienophile. Usually the dienophile is something that's, oops, that's not what I wanted, is something that's electron poor. It's got electron withdrawing groups on it. In the Diels-Alder reaction, you form 2 new sigma bonds and a new pi bond. You make a 6-membered ring. The Diels-Alder product is always, always, always a cyclohexene ring. And then you need to know some stuff about stereochemistry. So the 2 substituents that are cis to each other on the so-called dienophile end up in what relationship to each other in the product? Still got to be cis, right? That's required. Also, the 2 groups that are pointing outward in the S-cis conformation also end up on the same side of the new ring as each other. So you've got a couple of different options. One of the diastereomers is this one. The other diastereomer is this, where the functional groups on the original dienophile end up on the opposite side of the ring from the groups that were pointing outward in the diene. Of course, if the molecule you make is chiral, you expect to get both enantiomers, and the relationship between these 2 is that they are diastereomers. Okay? Yes?
Should we worry about preference between exo and metallic?
Should we worry about preference between exo and endo products? I mean, it sounds like you know that at one point you were worried about that. So thinking about things that you might see on the ACS exam, endo versus exo are words to describe these two diastereomers. You can assign endo exo here. It's a little bit tricky, and people generally don't. The term endo and exo came from this original Diels-Alder reaction where you took this cyclopentadiene, and then again, I'm just making up. Decided to do something different. Let's use this diene file with two esters on either side. You would make the new 6-membered ring, but this carbon here is sort of a bridge across that 6-membered ring. And then the two diastereomers were where those ester groups on the diene file were either on the same side of the cyclohexene ring as the bridge or on the opposite side as the bridge. And in this case, the way to assign endo versus exo is to look at the substituents on the diene file and ask, are they on the same side or on opposite sides as the bridge? If they're on the same side, that's exo. If they are on the opposite side, that's endo. And for reasons that may have been glossed over when you took the class, endo is preferred. There's some explanations for that we don't necessarily need to get into. Okay, that sort of refresh your memory. I think that's chapter 12, conjugation resonance diene. So if you need a bit of review on that, you can go to chapter 12 and learn some more. Okay, last thing I want to do is just talk about the Heck reaction, because I want to talk about how this bond is made and where the hydrogen goes. Again, I'm probably not going to ask you to reproduce this mechanism in its entirety. I do want you to know or recognize an oxidative addition step from a reductive elimination step. As I said, for the Heck reaction, you put these ingredients in and the active catalyst forms. Even though the starting reagent is palladium 2+, it turns out as the reaction gets started, that palladium 2+ gets reduced to palladium 0. It gets reduced by one of the phosphine ligands. Phosphorus-oxygen bonds are pretty strong. It's easy to oxidize phosphorus and use that reaction to reduce palladium to palladium 0. You don't need to worry about how that happens. Sometimes when chemists discover a new reaction, they don't know why it works at first. They don't know what the active catalyst is at first. With careful mechanistic work, however, people discovered that the active catalyst was not palladium 2. Instead, it was a palladium 0 that looked actually very similar to the Suzuki catalyst. So here is a palladium 0 species, 2 L-type ligands, the complex is neutral, palladium's a D10 metal, and there are 14 electrons in this complex, counting 2 in each of the metal ligand bonds. So we'll use the molecule that we used previously in our original example of the Heck reaction. The first step is oxidative addition of the carbon and the bromo group onto the palladium. Palladium inserts into the carbon-bromo bond. You form a new palladium-carbon bond and a new palladium-bromo bond. Of those two ligands, the bond to one of them comes from the electrons in the carbon-bromine bond, and the other two come from palladium. It's impossible to tell which bond comes from which source. All we know is that both ligands are now X-type ligands. They're bonded to the metal. That tells you that these are palladium 2. Palladium 2 is a D8 metal, and importantly, the complex has a total of 16 electrons overall, 8 on the metal and 8 from the 4 metal ligand bonds. That's important because that means there is still space for something else. So what happens in the next step is simply what we might call ligand binding. The alkene or the olefin binds to the palladium as an L-type ligand. What does that look like? Well, it looks like the pi electrons from palladium, both the 2 electrons in the carbon-carbon pi bond, sitting down on palladium and donating to palladium. It's hard to draw a bond with only 2 electrons between 2 carbon atoms and a 3rd palladium atom. I suppose you could imagine doing something like this, but then that would maybe allow you to lose track of how many electrons you were dealing with. So what we will do instead is we're simply going to keep the pi bond where it is, but we'll draw a dotted line to remind ourselves that that pi bond is a ligand on the metal. It's an L-type ligand because if that molecule left, it would just be the neutral alkene. We're still going to have over here the aryl group and the bromo, and then the 2 phosphine ligands. So now, if you're watching, we've got the 2 carbons that we eventually want bonded together are very close to each other. One of the things that the metal does is bring those 2 things close together. The next step is one that's weird, and I don't really expect you to understand it, but I want you to at least have seen it so you have some idea of how the reaction happens. This is called migratory insertion. What happens is the aryl ligand takes its electrons and attacks the terminal carbon of the olefin. At the same time, the electrons in that pi bond go and attack the palladium directly, forming a new metal ligand bond between the palladium and this internal carbon of what used to be our alkene. So after this reaction step, the new ligand bond is between the internal carbon of what used to be the alkene and the metal. We've got a new we've got a new carbon-carbon bond between the aryl orange carbon and then the blue carbon, what used to be the terminal carbon of the alkyne. And then the bromo is still there. So notice that that's formed the new sigma bond that we want, but it also got rid of the pi bond, and that's a step backwards. If you look at our Heck product from above, we want the new bond to be here, but we want the pi bond to be present too. So what happens next is something that palladium can do that you may not be aware of. It's an elimination step, and it's pretty similar to an NAD plus type oxidation. You've seen a hydride elimination in an NAD plus oxidation where electrons kick down and kick off hydride that's delivered to NAD plus. In a similar way, in this reaction, the electrons in the palladium carbon bond are going to kick down to form a pi bond, and then hydride gets eliminated but goes directly back to palladium. And that step is called beta hydride elimination. It restores the pi bond, it releases product, and it is selective for the trans configuration. There are reasons for that we don't necessarily need to worry about too much. Sorry, running out of space for our product. One of the reasons that we get the trans product is there are two hydrogens on the carbon. Only one of the hydrides gets eliminated. The metal eliminates the one that allows the ester group on the one carbon and the aryl group on the other carbon to not be eclipsed with each other. So steric sort of favors that arrangement, which results in the trans alkene. Then, after that beta hydride elimination step, you still have a palladium-2 species with now X ligands that are hydride and bromo. Reductive elimination regenerates the palladium-0 species and spits out HBr. And again, that happens, the hydrogen bromide bond comes from one of the metal ligand bonds, and then the other metal ligand bond goes back onto palladium, and that's where we get to palladium-0. And then the role of the triethylamine base is simply to remove the proton from HBr and drive the reaction forward. Okay, so that's the Heck reaction in a nutshell. I would like you to be able to recognize oxidative addition versus reductive elimination. You can do that just by watching metal oxidation states. Other than that, I showed you migratory insertion and beta hydride elimination so you'd have an idea of what's going on and not just view this as sort of magic chemistry. Okay, that is end of content. Now we're ready for questions. So what do you want to know? What's on the test? Everything. Yes, go ahead.
The last few reactions from chapter 28 should be on the test.
The olefin metathesis and cyclopropionation are not on the test. They might be on the ACS exam, but again, you can afford to miss 7 or 8 questions on the ACS exam and still be in the super high 90s of the percentile. So that's sort of factored in. Other questions? Yes?
How much are like actual mechanistic steps of like metabolism stuff?
Right, so how much of the mechanistic steps of the metabolism stuff are going to be tested? On my test, all of them. On the ACS exam, I'm not sure how much it's going to come up. Others? Yes? Yeah, my final, how much is new versus past? It's meant to be cumulative, though you will probably feel like it emphasizes the more recent stuff. That being said, the more recent stuff draws on previous stuff from chapters 13 through 16, so I think it's decently representative. The best thing you can do for the previous stuff is just focus on stuff that you got wrong or that you no longer remember. For the ACS exam, if you need some help reviewing, the end of chapter summaries are pretty good for just reminding you of what the reactions are. Yes?
If we take the ACS on Tuesday, we would need all our scores.
If you take the ACS exam on Tuesday, I'll have them scanned that day, the test scanned that day, and then I'll upload percentile scores later that day, so you should know by Tuesday. Yes?
That's usually for Saturday.
Saturday, it may be till Monday. It depends on whether the testing center will scan them for me on Saturday. I don't know. Others? All right, good luck. May the force be with you. Have a great summer. Yeah, my pleasure. You too.